Hey everybody, it's Tony from Adafruit, and I wanted to do a little bit of Python programming with the Raspberry Pi and play with some hardware. So there's an analog to digital converter called the MCP 3008, and I started to do a little Python library for it, and I wanted to kind of finish that process and walk through what's involved in making a Python library that talks to hardware on the Raspberry Pi, and maybe also see if we can put it on the Python package index, which is kind of the global place to put packages with Python. So if you've ever used the pip command to install a package, we'll try tonight and see if we can get a library up on the package system. So let me switch real quick to the desktop view. Oh, and you get a cool little OBS kind of freak out there. So the chip I'm going to play with is the MCP 3008. It's a little analog to digital converter that's interfaced with a simple SPI interface. So there's 4 wires that you need to talk to it. And this is great for the Raspberry Pi because the Pi doesn't have any analog to digital converter built into it. So unlike an Arduino, where you've got a few channels of analog to digital conversion, it's like you can read like an analog signal, from like a potentiometer, for example. The Pi doesn't have that. And so this is a really easy way to add a little ADC to the Raspberry Pi. So it's not super precise, it's only 10 bits, so that means it goes from 0 to 1023, which is 10 bits of data. But it's the same as like what an Arduino has that also has a 10-bit ADC. And it's real nice to add real simple analog sensing to this. You could hook up things like a thermistor that measures the temperature and changes its resistance based on the temperature, or like a light sensor, or like a photocell, for example. And so being able to access that from a Raspberry Pi and from Python is pretty powerful because you can build kind of interesting programs that look at the state of analog sensors and then do different things based on that. So let's see, let me get situated here with changing the scenes. So let's see, let's switch to my workbench here. So on the workbench, I've got basically the little Raspberry Pi Zero. I figured I'd show the Zero off because kind of this week and maybe next week also, there's a bunch of live streams that Lady Ada is doing to show off kind of Raspberry Pi Zero projects. So this is a cool thing to take note of. And I've got the chip right here. It's the MCP 3008, and it comes in a little DIP package, so it's kind of hard to see here, but it's pushed into this breadboard, and there's little tons of wires. I've got it kind of wired up to access all of the channels on it. And then below it, these are 2 potentiometers that I have hooked up to the 2 different channels that I'm reading. So this has up to 8 channels. So the top one here is channel 0, and the one below that is channel 1 on the ADC. And then let's see, let's go back to the desktop view. And so like I was showing before, here's the chip. It's in the store. Nice thing also, it's really cheap. It's like a little bit under $4, so it's not a huge expense to add this. There are a lot better analog to digital converters you can get. Things like the ADS 11115, they're like 16 bits. But they're usually a little more expensive, and you don't necessarily need it if you're just reading like a potentiometer like I am here. And I'll also show, so I'm connected to the Raspberry Pi here, and we'll come back and we'll look at the code that I have so far. But we do have some code right now to use this this analog to digital converter. We have this older Raspberry Pi Python code. And so if you've done a lot of Python stuff with Adafruit's boards and sensors and things, you might have used this code. And what we want to do is actually break a lot of this code out. So originally, all of the drivers for Adafruit's Python stuff was put into this one repository, which is nice that you can get all the code at once. It makes it a little bit simpler. But the tricky thing is, if we want to put this on the Python package index, we really just need each one of these to be an individual repository. It has to have some certain metadata set up to say that it's a library. So what we want to do is actually break all of these out into individual packages that live on GitHub, and then also the package index. And we've kind of started that already. So things like the character LCD, I have a newer character LCD library that kind of shows how you can use it with like the BeagleBone Black and the Raspberry Pi. Things like the DHT humidity sensor, that one we've broken out also. So I'm kind of going through and doing the last ones that we haven't really broken out already for these. And so the MCP 3008 is one of those sensors. And the code we have right now is actually really simple. It's not a library, it's really more of just an example of here's how to talk to the chip. And we'll look more at that in a second here, but it's really just using the SPI serial interface to talk to the chip. You send it a real simple command that says what channel you want to read, and then it responds back with the value that it read from that. So that's really all the functionality in here right now. It actually uses the GPIO on the Raspberry Pi instead of using the hardware SPI interface. I'll show you in my library. I've made some updates so that we can actually use the hardware SPI interface if we want. You can also use the GPIO, but that's why this implements its own SPI write functions. So it's actually doing the physical SPI protocol to read and write data, but by toggling GPIO pins on here. The actual core of this is really just calling this read ADC function here, and then inside of this function is where it has all the logic of talking to the chip. So what I've done is I've actually started to break this out. So I created this Adafruit Python MCP 3008 library. It's on our GitHub repository, and I've made it more into a proper Python library in the sense that you can install it, you can access it from other scripts. Like, you don't actually have to have the code for this in the same directory as your Python script that you're writing. So it's a little bit more like a library that you might pull down from pip, and that's the eventual goal that I want to get with this, is actually to put it on the package index that Python has, so you could just do a pip install Adafruit MCP 3008 and it's all ready to go here. And so the code for this, let's see, let me switch to my text editor here, and we'll bring up the code that I've got on the Raspberry Pi. Okay, cool. So I've got the code, and also let's see, let me connect to the Pi and we can run the little example code that I have here too. So let's see, let's switch to the desktop view. Yeah, here we go. Actually, let's do this one. So we'll see all of these. Actually, let's do the desktop view here. So, okay, so I'm connected to my Raspberry Pi. I've just SSH'd into it. And basically, I'm inside the folder for this MCP 3008 library, and I have an example in here. It's the simpletest.py. So I'm going to run this example, and this is basically going to go and read all of the channels and print them out in a loop. And this kind of, okay, yeah, there we go, simpletest.py. I pressed tab, but for some reason, sudo python simpletest.py is what you need to do. So we run this, and you can see it's printing out. So these are all the channels, channel 0 through 7, so 8 channels. And this is every half second it takes a new sample. And so this is showing the raw analog to digital converter value. So this value is going to range from 0 to 1023. And if it's 0, then it means it's like 0 volts of input. And if it's 1023, then it's 3.3 volts of input. So it has that kind of range of values. I'm going to tweak some of the knobs here. So this is channel 2, and I'm going to turn it all the way up. So you can see it went up to 1023 down here where the most recent samples are. If I turn it down, it goes all the way down to 0. And same thing for channel 1, so I can turn it up and turn it down. So pretty simple, easy to kind of read this data here. And I'll show you the code for this example now. So let's switch over to the text editor, and in my examples folder, and I'm just connected to my Raspberry Pi using SSH. Like Ubuntu has this kind of fancy thing built in where it can actually create a little file system that my text editor can access. So whatever I edit on my computer here is actually just being sent over to the Raspberry Pi. And by the way, so I think someone asked about if there are other programs for that. I found a really nice program, FileZilla, that's actually cross-platform, and it's normally used for like accessing an FTP site, but it also supports SSH file system, or I think SFTP. And so what you can do, you can set it up in this little site manager. So I created a Raspberry Pi, and you just give it the host name or the IP address of your Raspberry Pi. You want it to say it's the SFTP, SSH file transfer protocol, and then set your username and password in there. And then you can connect to this, so I can connect to my Raspberry Pi. And over here it's going to show files on the Raspberry Pi. So like here's that MCP 3008 directory that I'm in. And the cool thing is you can actually set this up in its settings, in the preferences. You can give it a default text editor that you want it to run. So I told it run the Atom text editor, and this I can actually click on a file in here like this README and edit it directly, and then whenever I make a change and save it, it'll go back in and write it back to the Pi. So I'm not actually going to use this, but I just wanted to point out it's a good example. Like if you're on Windows or Mac OS 10, you could use a program like FileZilla. Even Linux, it's also available on that if you don't have like Ubuntu here for it. So still being edited. Sure, yeah, let's close it. So okay, back to my example code here. So this is the example that I was just demoing, where it's printing out every half second all of the ADC values for all the channels here. and it's pretty straightforward as far as the code. So we just import the libraries that we need to use. Then we go in and we configure which pins I have connected. So this is setting the clock, the data output from the chip, the data input to the chip, so things that the Pi sends to the chip. The MOSI, that's master out, slave in. MISO, master in, slave out. It's kind of a way to say like which way the data is going. And then CS is the chip select, which kind of says, okay, we're ready to talk to this chip now. So I set all these pins to how I have them wired on the Raspberry Pi, and then I pass those into an MCP 3008 object constructor. So I just say exactly what those pins are. I can also set this for the hardware SPI interface, where the Raspberry Pi and a lot of other Linux boards can natively talk this SPI interface. And the advantage of this is that it can talk at really high speeds. Whereas when I have this configuration up here, it's actually just using any GPIO pins to do this in software. So it's called bit banging, where it manually drives the pins high and low. Like the clock pin, it's going to drive that up and down to send and receive data. So there are trade-offs to each. Like the software configuration, you can use any GPIO pins. So as long as you have 4 free pins, you can use those to talk to a device. Whereas the hardware configuration, you're usually limited to some specific set of pins on a board. So for like the Raspberry Pi, it has 2 channels with the SPI that you can use. So you can have up to 2 SPI devices on the hardware interface. So in this case, we don't really need a fast clock rate to talk to this device. So the software SPI is fine. But it is nice to have the flexibility for this hardware SPI. And I'll show you how this works in a second. But basically the main loop of this program is just printing out all of those samples, and it looks a little complex, and that's mostly just these print statements where this just prints out every single channel. So basically I'm using the Python string formatting code where you can say, okay, this value inside of the curly braces will actually get replaced by a value that you send into this format function. And so this is actually printing out the values 0 through 8. It's giving you the nice little column headers at the top here. So like these values right here is what this line's printing out. And then the actual core of the loop is I go through and I read each of the ADC channels. So I go channel by channel, so through all 7 or all 8 channels. So this goes through the values 0 through 7, and I just call this read ADC function, and I pass in the channel value, and it'll output the value that it read from that channel. And I store those into an array, and then I print them all out just like I print out the headers here. So this is printing out this value here, and instead of passing in all the numbers 0 through 7 like I do here, I actually pass in my array of values. So it's a little maybe complex looking in the code, but that's one nice thing about Python, where you can really pack your functionality down into like one line. You know, I could do a loop that says, okay, print out the first value and then print out the next value. But this is kind of nice in that if I put all my values into an array, I can send them into this string value. And this little star operator, you might not see this all the time in Python, but it's a super handy thing where it's an unpacking operator where you pass it an array, and it'll actually take all the values in the array and pass them as parameters to whatever function you're calling. Because this format call could actually take values like 0, 1, 2, 3, and it's going to go in and say, okay, value 0, I'm going to put into the 0 curly brace here. But I don't want to do that. Well, I could do that actually. I could pull out each of the values I've saved. But since I have an array here, I'll use the star operator and say, okay, unpack all those values and pass them in as parameters. And so that's one nice advantage about Python, is that you can write really succinct code that does a lot of things. It can also hurt you too, in the sense that, you know, when you first look at this line of code, it might not be super obvious what it's doing. So you kind of have to be a little familiar with some of the specifics of Python. So that's how we use it. Let's maybe jump in. Well, actually here first, let me show off the hardware SPI also. So I actually have the pins hooked up on here to the hardware SPI channel 0 on the Raspberry Pi. And I can access those using GPIO like I did above here by just using these pin numbers. But if I uncomment this, then I'll access them using the SPI device. And if I go back to the Raspberry Pi here, so the SPI device itself is actually in the Linux kind of root file system. So it's under the /dev/SPI hierarchy. And so you see there's a SPI-dev 0.0 and SPI-dev 0.1. And so what that means is it's SPI-dev channel 0, I think it's channel, I can't remember the exact terminology, but basically there's one SPI interface on here, so it's interface number 0, and then that interface itself has 2 chip select pins. So there's, or chip enable you might sometimes see, so there's chip select 0 and chip select 1, and that's what that other thing after the dot is. So I'm hooked up to chip select 0 on SPI interface 0, so I'm actually using this SPI dev 0.0, and that's why you see this configuration here. So I have to say, I guess it's the port is what they call it. So port 0, which is that first dot, and then device 0, which is the second dot after that. So since I have that configured, I should just be able to run my example again, and you can see it works just as it did before. So that's kind of cool that you've got that flexibility here where you can just choose, if you want to use a software or a hardware SPI interface for this. And like I said, there are trade-offs to each. So you have more flexibility with the software SPI, but less speed in this case. So, and let's just kind of dive into the code real fast. And maybe before I do that, I'll start with just a quick little explanation of what it means to be a Python package, or how I've created Python packages for a lot of the libraries we have. So the big thing to make a Python package is that you need to have a setup.py file. This is used by setup tools and distutils, which are 2 packages in Python. There's a long history to them, and I don't even understand everything to them, unfortunately. They were actually kind of competing projects for a while, and I think eventually they merged in the recent years or so. But the end result is that you need to create this setup.py, which calls this setup tools functionality to actually install your library. It can do lots of things. It can upload the code to the Python package index, but we're really using this to just install the library so that once it's installed, you can write any Python script that imports your library, and you don't have to mess around with making sure your code is there. It gets installed into a global place. This also works with things like if you're a little more advanced Python programmer, you might sometimes create a virtual environment where it's like a virtual Python that has its own set of libraries, and so because you create a proper library like this with a setup.py, you can install things into that library. And the contents of this, so I won't go too deeply into this. I will just say, if you want to learn about this, the best place to go is this website. It's the Python Packaging User Guide. So it's Python Packaging User Guide.readthedocs.org. Just Google search for Python Packaging User Guide. This is basically the definitive source for Python information around how to package up things into libraries. It's really nice. There's a lot to read here, unfortunately. So I'll try to kind of give you the highlights of this. But we'll come back to this in a second too to learn about how we put stuff on pip. So the setup.py really just needs to call this setup function. It gets this setup function by importing it from setup tools. I also do something kind of fancy here in that I use this easy setup.py, which I actually didn't write. It's a utility that's sometimes provided. And what this does is it'll actually go in and download this setup tools library in case you don't have it. It'll install it so that you can make sure that after these 2 lines of code run, you'll have that installed. I don't know if that's strictly necessary anymore. I think later versions of Python actually include setup tools now, but I kind of put this in just because it seems safe. In case someone has an older version of an operating system, this is nice, and it'll make sure it's in a good state that lets me use setup tools. So I call the setup function, and there's just a lot of metadata that you have to pass in here. So you give it like the name of your library, the version, who created it, where to find it on GitHub, that type of stuff. Now the one interesting thing is this install requires. You can actually list other Python libraries that need to be installed before your library can be installed. And in this case, I'm actually depending on this GPIO library that I'll talk a little bit more later. This is a little wrapper around things like the SPI interface, GPIO, and it tries to abstract away platform-specific stuff. So like on the Raspberry Pi, you can use the rpi.gpio library to access GPIO. But on the BeagleBone Black, for example, there's the BBIO library. There are lots of different libraries. I think on the Raspberry Pi, there's also a new Pi 0 or GPIO 0 library. So the tough thing is, if I wrote this MCP library to use like the rpi.gpio library, it would be locked into that. It would be Raspberry Pi only. So I built this little GPIO library that's kind of a layer above GPIO libraries like rpi.gpio and BBIO. and it'll pick whichever library it should use depending on the platform. So it'll look and see if it's running on a BeagleBone Black, it'll pick the right library on that platform. If it's running on the Raspberry Pi, it'll pick the RPIO, GPIO library. So it tries to do the right thing and let you write code. So now in my library, if I code against my generic GPIO library, then it'll run on anything. And if I add other hardware to this GPIO library, in theory, this MCP code should just work on that new system. But anyways, the install requires, this is where you can call out, like if there's certain libraries you depend on, and I just really depend on the GPIO library, so I don't need to add other stuff here, but you could just add them in as the list values. And then this packages value says what Python package to install, and it actually calls this find packages function, which is a part of setup tools, and that will actually look at my directory and see which Python packages I have and then include them automatically. Otherwise, you can just explicitly call out, I think it just takes a string here where you say the name of the package, but it's kind of the convention in Python that you call find packages and you structure your library so that at your root level here is where your Python package is, that's your main library. And that's what I have in this MCP 3008 folder here, is that this is the actual Python package that implements my library code. And the thing that makes this a Python package, and actually let me go into the Pi itself, and let's this might be a little bit bigger and easier to see. So what makes this a Python package is this init.py, which there really isn't much in here. I'll come back to what's in here. But when Python sees this __ init __ .py, then it treats that directory as a Python package. And so I can actually import this from a Python script. Like if I had a script in the same directory, actually go up above, if I had a script in this directory that imported Adafruit _ MCP 3008, that would work because I have this init.py. So it's super important. You'll see it a lot in Python code, and at first it's kind of weird. It's like, and a lot of times it's a blank file. You might scratch your head and wonder why all these files are there, but that's kind of the convention for how Python identifies this stuff. And then inside of here I have the actual code in this MCP 3008.py, and so we'll look at this over here. And this is actually my library code. So I'm basically just creating a class and then adding some functions to it that let you talk to the ADC. So like here's the read ADC function that I was using in the example code, and here's kind of the implementation of it. And let's see, let's go back up and I'll kind of go through what I'm doing in this code just from the start here. So the init function, this is the initializer. That's, think of it like the constructor. When you create an instance of this class, it can take in these parameters and it'll set the class up to work. Now there's a little bit of complexity here. Basically, because I'm supporting either software or hardware SPI, I have to figure out here what the user is trying to do. So all the parameters I can take in either an explicit clock, chip select, MISO, MOSI pin, and if you give me those 4 values, then I'm going to assume that you're using software SPI, or you can pass a SPI device here, and if you give me that, then I'm assuming you're using hardware SPI, and that's kind of what we saw in the example here. So in the example, when I use hardware SPI, I send in the SPI value, and I set it to the SPI device that I create based on the port and the device here. Versus when I use the software SPI, I'm just passing in those 4 pins explicitly here. So that's what's happening here in this initializer and this block of code specifically. So I'm looking to see if you passed in a SPI object, I'm just going to save that and use that internally. If you didn't pass in a SPI object, but you did pass in all 4 of these GPIO pins, then I'm going to actually create this spy.bitbang object, which that's the software SPI implementation. And I'm going to pass it all those pins. And if you didn't pass, like if you forgot to pass in, the MISO line, for example, it's going to fall through to this else and actually just throw an error that says, hey, you forgot something. I can't tell if you're trying to use hardware or software SPI here. Once I have those, I set the clock speed, the mode, and the bit order for the SPI device. And basically the clock speed is how fast we can talk to the chip. And actually the chip itself, another super handy thing, whenever you're porting code over to Raspberry Pi, you're going to want to go straight to the datasheet. So this is the datasheet for the MCP 3008. And if you dig through this thing, it's a little bit of digging. They usually say what the max clock rate is, and it's in this big table. So here's the timing parameters, the clock frequency. So it can go from 1.35 megahertz up to 3.6 megahertz, depending on the voltage passed into the chip. So I'm running at 3.3 volts. So, I could probably do about 2 megahertz. But I decided to play it safe, and I actually stick with 1 megahertz as my speed. And actually, if you read this data sheet, they kind of bury it in here somewhere. Yeah, so it kind of warns you. So you can go slower. Like this is a max value of the speed. It says the effective clock rates below 10 kilohertz can affect the linearity of the performance. It's basically telling you don't go slower than 10 kilohertz, which that's okay. So I'm safe to use a megahertz. One thing to know though with Hardware Spy, usually you might not you can't specify the clock rate to an exact value. Most hardware can only do like powers of 2 or maybe powers of 16 or something sometimes, or just crazy values where I might ask for, I want like 1.8 megahertz, but the chip can't actually do that. And in my SPI GPIO library, I actually pick the best available clock speed that's not faster than what you specified. So I'm asking for a megahertz here. I might actually be getting less than a megahertz. So it's just something to be aware of, that you might not get the speed that you want in some cases, just due to the limitations of hardware. The SPI mode, so this is actually kind of funny. I noticed Google has, when you search for SPI mode, it doesn't come up anymore. But sometimes it would actually parse out the data from Wikipedia. It was kind of neat. It showed a little table. But in the SPI protocol, there are different modes that you can have, and those change whether the clock is at a high level or a low level. It changes when it reads the data, if it's at the rising edge of the clock or the falling edge of the clock. It's something that you need to look at the data sheet to see. I can't actually remember where I saw in the data sheet this value. But most devices use SPI mode 0. Sometimes they get more advanced. There are 4 modes, and basically look in the data sheet and you'll find out what mode to use. But I'm just explicitly specifying it here. And then the bit order is just how to interpret data that comes back. Is the most significant bit coming back first, or is the least significant bit coming back first? And so I have the 2 values you can specify here, the LSB or MSB values for this. So this chip uses most significant bits as the bit order for this. So that's all I do in the setup here. I'm really just setting up that SPI connection, whether it's a software SPI connection and I need to create it by bit banging the GPIOs, or I save the hardware SPI connection. And if we want to look, I can real quick as a detour look at the Python library. So this is my Python GPIO library that I was talking about. It's basically a layer above all the GPIO libraries that we have. And in this spy.py file is where I implement all this code. And so here's this SPIDEV hardware device that we saw in the example code here. So when I'm creating this SPIDEV device, it's actually coming from this class here. And you can see it implements setting the clock speed, it implements setting the mode, that type of stuff. And then also in this file I have the BitBang implementation. So this is the BitBang implementation that we saw in the actual code for the class, where if you pass in all the GPIOs to use for software SPI, it's going to create an instance of this class. And this one actually goes through, and you can see it's just toggling the GPIO, like when it's reading data, for example. It goes through, it sets the chip select for all the bytes, it toggles the clock up and down. So that's one nice thing. And then I've put this all into one library that all of my other libraries can use. So I don't need to rewrite this software SPI implementation in the future. It's in one place, less chance for it to, break. Like if I'm copying this between other libraries, if I want to make edits to it, it lives in one place. That's kind of nice for this. So that's the basic code. Let's see. Let's jump into maybe the read ADC function. So we'll look at what we're doing here. And before I do this, actually, let's look at the data sheet. So we'll jump down in the data sheet and kind of look at the specifications for how to talk to this chip. So at the start of the data sheet, it's kind of showing all the characteristics of this chip, things like how its ADC performs, that type of stuff, like what kind of noise it has. A lot of this stuff isn't interesting to me right now because I'm just looking at how to interface with this chip. So I'm going to scroll all the way down to the device operation. Actually don't need this info right now, but this is good to read. This kind of tells you how the chip works and what kind of modes it has. But the actual serial communication, so this is what I care about. So this section is actually talking about how to talk to the chip over the SPI interface. And it's really straightforward in that you basically just, when you want to read a channel of ADC data, you start a SPI communication with it. Like, so you basically change the chip select pin. You pass it a few bits. So it actually says in the paragraph here, you pass it a start bit, so a value of 1. Then you pass it a bit that says whether you want to do just read a single channel or whether you want to read a differential input, where it can actually take two channels and subtract one from the other and give you that difference value. And so that's what you pass as the next bit, either a 1 or a 0 to pick those values. Then you actually pick the channel itself, so the D2, D1, D0, so like channel 0, channel 1, and luckily in binary, this is just the actual value of the channel. So like channel 7 is the value 7 in binary. And that's what you do. And then it actually says in this paragraph, you need to send it another clock and ignore whatever data is there because it's actually taking the sample during that clock. Then you send it another clock and it'll send back a 0 value. And then you send it 10 clocks and it'll actually send you back the 10 bits of data. And they have this in a nice little diagram down here that actually kind of shows you what it's doing. So like here's the start of a transaction. And so this is the start bit. Here's where you pick whether it's just reading a single channel or reading the difference. Here's where you send the channel ID. Here's this blank kind of waiting for the sample to be taken clock. And then here's the null bit that it sends, and then the 10 bits of data that it sends inside of here. And all of this happens within one SPI transaction, which means we've flipped the channel select bit, or it's gone low basically for this, and it stays low for this entire operation, and then it goes back high again. And then during that time, we toggle the clock, and I think it's on the rising edge of the clock that it's actually reading these values. I can't remember exactly for this mode what it's using, but basically, we kept that CS pin low, we toggle the clock, we send the data at the start, and then we read the data. So it's important to note, like we don't drop the CS, or we don't set the CS pin high again after we send it which channel to read. It doesn't turn into like two transactions, for example. And I'll show why this matters in just a second, because it kind of complicates things. Like with SPI devices, there are lots of different ways you might interface with them, where like some devices might want you to send them a byte of data and stop that transaction, then create a new transaction to read the data. So it varies by the chip and changes how you kind of have to interface with it a little bit. So if we jump to the code, we'll look at the read ADC function now. So this one just takes in the number for the ADC you want to read, like which channel, 0 through 7. And then in the code, I'm really just doing a quick sanity check to say, okay, let's assert that that value is actually within the allowed range of values and throw an error if it's not. It's always smart to do this, especially when you're writing a library that other people are going to use, because you might get some bug and not realize that you're passing in a garbage value here, and maybe it works randomly and then it stops failing. So wherever possible, sanitize your inputs, check that they're good, that they're values that you allow. And then I basically build a read command that I'm going to send to this. So like we saw in the data sheet up here, I need to build up these bits right here that I'm going to send to this chip. And so that's what I do. So I start with 1, 1, and so this stands for the start bit value that I need to send in. So that's the value that we saw down here. So the start bit is always set as 1. Then I send it a 1 because I'm reading the just a single channel, and so it tells me to use a value of 1 here. And then I shift those up 6 values, 6 positions. And the reason I do that is because the SPI API is based on sending bytes around. So you can't just send a bit of data. You actually have to send a byte. And so I need to pack my operation into a byte and say, okay, the first 2 bits of this byte are going to be 1, 1. The next 3 bits of this byte are going to be my channel value. And then I'll actually have 0 as the last 3 bits in that byte. And so that's what I do in this operation here is I say, okay, I've got my 1, 1 shifted over 6 positions so that it's at the very top of my byte. And then I'm going to slot in the 3 bits for my ADC channel. And so I'm ANDing my ADC number by OX7 because if I go to the calculator, you'll see OX7 actually equals 111 in binary. So this is a super handy thing also, is to have a good hexadecimal calculator. So 07 equals 111. So this is going to pull out the 3 low bits of my ADC number here. and then I'm going to shift those over 3 positions because I still have 3 extra bits in this byte left. So, for example, if I'm reading channel 0, channel 0 equals OB, and this OB is the Python syntax for making a bit literal byte. So you can actually specify the 8 bits as ones and zeros in here. So 1 1 0 0 0 0 0 0. And so just like I was saying before, this 1 1 is the start bit and the single channel read. This 0 0 0 is which ADC number I'm reading. And then these zeros are actually bits that are just going to be swallowed and ignored. But I need to pass these because all of this has to happen in one SPI transaction. And so that's what this transfer function is doing, that I'm passing it an array of 3 bytes. So I'm passing it my command byte that I set above that, for example, might look like this. And then I'm sending it 2 more bytes of 0, 0. And the reason I do that is because during the SPI transfer, it's going to actually flip that chip select bit and hold it at for all 3 of those bytes that are transferred. And so that's why we can match up, or that's how we match up to the communication that we see here, where I'm sending the data, the chip select is still held low, and then I'm reading the data here. And the transfer function basically does a send and a read at the same time on the SPI bus. So I'm sending this first bit of data, and then I'm sending a bunch of zeros after that. It doesn't matter that the chip is going to ignore those values that are sent here from DN. It actually says it doesn't care about those values. So it's okay to send those. But at the same time that the Pi is sending those values, it's also reading values. So it's going to read the values that come back from the chip here. And so that's what those extra zeros are. So those zeros stand for the extra clock cycle I need to let it do the ADC sample, the null bit, and then the 10 bits of data to actually read it back. And unfortunately, because the SPI interface only works a byte at a time, it's actually not an even number of bytes here. So I have like my start bit, so that's 1 value, what type of operation I'm doing, and the 3 bits of the channel, so that's 5 bits. Then I need to waste a bit just to wait for it, so that's 6 bits. There's the null bit is 7, and then I have 10 bits of data to read, so that's 17 bits of data. Doesn't fit nicely into bytes. It's 1 bit over 16 bits, which I could do as 2 bytes. So for that reason, I have to send 3 bytes of data. So I'm sending extra zeros. Now, luckily, that's okay because basically, if you read the rest of the data sheet for the chip, it says that after it finishes clocking out data, if it gets extra clocks, it will actually just repeat the data again. So it means that I can send it extra clocks. It's kind of wasteful. It's kind of annoying, but it's not like I can read this chip at tens of megahertz. It's got a limit to how fast I can read it. So it's not the end of the world if I have to send it a few extra bits and just throw them away to work with this interface. But again, it's also maybe a good limitation too of things like the SPI interface. Like if I'm using the hardware interface, on the Pi and in Linux, it's built to work only with bytes. I could technically use a software interface and read 17 bits of data, but I didn't implement that in my library because I want to allow you to switch between hardware and software, and so it's hard to rationalize the difference between those two. If you really absolutely had to read 17 bits of data, I'm not sure the Pi could technically do that with its hardware. You'd probably have to write your own bitbang version that just talks to the chip directly. Let's see. I noticed this question. Does writing work the same way? Like writing in the sense of reading? It does work kind of the same way, at least all the SPI operations here. So maybe I'll go through some of the SPI operations that you can use, but like this transfer function, for example, it sends and receives data. And so when it sends data, it will pull down the chip select line, it'll toggle the clock, and then it'll send out on the data output line the data that you're sending. When you read data, exact same thing happens. It pulls the chip select down, toggles the clock, and then it reads in data. And then the transfer function does both at the same time, where it'll pull down the chip select, toggle the clock, and then it'll read and write data at the same time for this. So that's why I do this transfer function, because in a single SPI transaction, I need to send data and read the data. Now, after I get a response back, then I pull out my 10 bits of data that were returned. And so I'm pulling the first bit of the first response, because basically that's the 8th bit, which ends up being this B9 value here. So there's 1, 2, 3, 4, 5, 6, 7, 8. So I need to pull this bit out. Then I need to pull the next 8 bits out from here. And then I need to pull out one more bit after that, or 2 more bits actually, from the last byte that I got back from here. So ultimately I get 10 bits of data, and that's what I'm returning here in this result. And I'm doing all this ANDing because, like I mentioned before in Python, its default numeric type is a 64-bit integer. And so you run into trouble when you want to restrict something to be like a signed or an unsigned value within a smaller range. You basically need to do an AND operation to say, hey, I just want to mask out these bits. Otherwise, if you have like a negative value, Python can do some crazy stuff. It'll extend the sign bit and you'll get wacky values. So you see this ANDing a lot in Python code, and that's basically what I'm doing is I'm just masking out the only the 10 bits that I care about here. So that's all I'm doing to read the ADC here. Basically I'm using this SPI interface, and like I said before, it's all a part of this Python GPIO library that kind of wraps around the SPI interface, and it implements like a software SPI. As far as the functionality that we have, so like I mentioned, there's the transfer function that's in here. So that does like a full duplex read and write. It just means that it's sending and receiving data at the same time. There's also a read function which lets you just read in data, and then a write function that lets you just send data in here. And those are the basic operations that you can use with SPI in here. There is another type of transfer. I don't have it implemented. So like if you use the Python SPIDEV library, which is what this uses internally, that's kind of the Python interface to the SPI hardware. It has a transfer and a transfer to function. It actually calls them exfer. There's exfer, exfer2. And the only difference between those is how it toggles the chip select. I think in one of them it toggles the chip select between maybe the reads and the writes, or I can't remember exactly what the difference is, but in some cases there's some SPI hardware that cares about how you're toggling the chip select lines, and so you do sometimes have to get into the gory details of that. And again, it just comes back to the datasheet. Your datasheet's going to tell you how this SPI device works, and especially if you look at these diagrams, most datasheets have a diagram that shows, here's all of the pins, and here's an example of like sending data or receiving data. And so in here you can see like they hold the chip select line low for all of it. So okay, cool. So I think what I want to do next, there's one bit of functionality. So with this library, I've implemented everything that we had in the old Python code for this. So this is in that Raspberry Pi Python code, that MCP 3008.py. This really just gave you reading the ADC. One thing I noticed when I was looking at this ADC, though, like I kind of saw before, it has this differential mode where it can actually take the difference of 2 analog inputs and give you that value, which can sometimes be interesting. Maybe you have 2 signals, maybe 2 different sensors, and you want to see how they differ. This is good, for example, like, the way my ADC is set up right now, it can only read values between 0 and 3.3 volts. But what if I had 2 really large signals that went beyond 3.3 volts, and I only wanted to look at like maybe the difference between those 2 signals, and I knew that difference would be small, like within that 3.3 volt window. I could potentially use like the differential mode here. So I was thinking, let's implement the differential mode real quick, because it's actually not much more code than what I have here. So I was thinking, let's add like a read ADC difference function, and you could pass in the channel. Now the functionality changes. So for your channel select, when you select channel 0 in this difference mode, it's going to give you channel 0 minus channel 1. If you pick channel 1, it's going to give you channel 1 minus channel 0. So basically channel 1 and 0 are kind of paired together here, and then which one you pick depends on which one you want to be subtracted from the other. And like channel 2 and 3 are kind of paired together, 4 and 5 and 6 and 7. So really all I need to do to make this work is to just change how I talk to the chip, and instead of sending it a 1 for this single or differential mode, send it a 0 here, and then I can pass in the exact same channel select number here, and then it's going to give me back a value that's the difference of those channels. So what I wanted to do to start with this is, I think I can just copy this function and make a little tweak to it, and it should give us the results we care about. So I'm going to call this read AC difference, and let's call this, I think they call it differential in the data sheet, because it's not technically the channel. You're picking from pairs of channels which one you want to subtract from the other. The naming is sometimes one of the hardest things, is trying to figure out a small name that describes what you mean. So read the, let's just rewrite this completely. So read the difference between two channels. Differential should be a value of, I'll make a little table in here. So 0, say return channel 0 minus channel 1, 1, channel 1 minus channel 0, and then let's just copy these, oops, and paste them, and we'll fill in the values. 2, 3, I think I have 4 of them. 1, 2, 3. Yeah, that should be enough. Oh wait, no, that was too many. Yeah. Okay, so let's do 0, 1, and I think this works with 2, 3, 3. Oops, yeah. Here, actually, let me write this the right way here. So 2 minus channel 3, and then this should be 3, 3 minus channel 2, and let's actually check that real fast. Data sheet. So yeah, 2 minus channel 3, 3 minus channel 2. So yeah, that's the way they do it. And then this is going to be 4 minus channel 5, 5 minus channel 4, and then this should be 6 minus 7, and 7 minus 6. And then all of these are just increasing, so 2, 3, 4, 5, 6, 7. So let's just double check. So channel 7 is 7 minus 6, yeah, like I had there. So, okay, and I just like to do this in Python. I really like to have good doc strings because that helps you understand, what this function is supposed to do, and it also can just turn straight into documentation for code. And maybe I'll show that in a second too, is how you can actually see the documentation for this class. So I've got that set up. The values are exactly the same. I take a value from 0 to 7. Maybe we'll just change this to be correct. We'll say differential number must be value from 0 to 7. Now let's build a difference channel read command. And then the one difference I just need to make here, so this is my start bit. This is the bit that says whether I'm doing a single channel or a differential read. So we'll change this to differential. And everything else should be the same. So I'm going to pass in the ADC value, do the exact same shifting, get the same value back. So let's save that, and let's actually create a new example to demonstrate this. So let's make a differential.py, and we can actually just copy all of the code from my simple test, but we're going to change this one a little bit. So let's actually, simple example of reading using its differential mode. We'll print the difference of channel 0 and 1. So we'll just start with one channel for now. I'll keep the configuration the same, so you can pick whether you want to use hardware or software SPI. And now here, let's just totally change this code. So let's go in and we'll loop forever, and we'll sleep. Time.sleep. So every half second we'll print things out. And maybe just to start, let's just call it, and let's do my MCP dot read ADC difference, and we'll do 0. So this should take channel 0 minus channel 1, and then let's print it out, and we'll say channel 0 minus 1, and we'll do this as a format string. We'll print that value out. So let's save that, and let's actually go in and run this. So sudo python differential.py. Oh, okay, I messed something up here. And this is also why I like to write a simple test. Before I get too far into this. I want to have a real simple script that actually tests the change I just made. So this is telling me global name ADC number is not defined. And yep, of course it's not defined because I changed the name. So right here it's saying I'm looking at that ADC number value, but I changed the parameter name here. So let me make this match. So let's save that. Let's see if this runs now. So, interesting. Let's see. ADC number is not. I should probably check. Oh, here's a cool thing, actually. I'll show you. If you're using Atom, so I'll go back to what I had before. A lot of text editors have this. They sometimes have a multi-select mode where if I select something in Atom, if I press Control-D, it actually goes and figures out which other instances of that I have in the file. So this is kind of handy if you just want to check and see, like here in this function, I know, okay, these are the two instances, and I can actually change these both at the same time. So we'll say differential, and now I should have both these set. So let's see this run. So okay, cool. So it's telling me the value between these is 0. Now, the reason that difference is 0 is because I actually have both of these potentiometers set to just about the same value. I'm going to crank my channel 1 all the way up to 1023, and then I'm going to crank this one down. And oh, interesting. I don't think it's actually reading values out here, or at least I'm getting a bad value. So let's see. Let's debug. Oh no, sorry, I turned it down. Maybe. Oh, interesting. Let me cancel this. I just want to check, see that this thing's working. So let's do. Oh wow. So I'm getting all 0 values now for this. Well, okay. Let me go back then, and let's actually debug this a little more. So let's go back to simple test. Something just changed in what I've done. I might have broken it somehow. Let's jump back. Let's ignore Hardware Spy for now. Let's go back to Software Spy and see if this is working. And we might need to come back and see what's up. Okay, so Software Spy is working. I must have done something a second ago that just broke the Hardware Spy. So let's go back and see if there's anything obvious for this. I don't think I changed anything here, so that's really odd. I'll have to come back to this and investigate this, but let's just move forward. We'll use the Software Spy. So again, this is just simple test. This is showing, I just cranked up channel 2 to 1024, and let's go back. Let's move these about to kind of similar values. Okay, now let's change our differential test, and let's have it use Software Spy for now. That's still kind of bizarre. I'm not sure what I just did to break the Software Spy or the Hardware Spy. Okay, let's run the differential mode. Now it's telling me the difference. So I'm going to crank channel 0 all the way up to 1024. So now its value is 1024. Channel 1 is around 500 or so, like we saw before. And so this is taking that difference and showing me that the difference between those two channels is 512. So if I crank channel 0 all the way up to the max, then it's going to go down also, and we'll see kind of fall. Or I can crank it up a little more so that now my channel 1 is set to 0. So the difference between those is 1023 in this case. So just kind of neat. You can see how differential mode works there. So I've got differential mode. Seems to be working. Let's see. Let's go in now and let's look let's just see if I can get this Hardware Spy working again. It's kind of bizarre why it stopped. I'll just spend a second here. Let me make sure I have the speed set correctly. I've got the pins and the ports set correctly. Just see if there's make sure my spy devices are still there. Yep, those are still there. So I'm setting my clock rate to a megahertz, mode 0. The bit order is most significant first, which that should all be correct. Let's go back to my example here, and let's see. So yes, port 0, device 0. Let's just try this one more time and see what it was that I seem to change on here. So let's see, let's save that. Do the simple test. That is bizarre why it's not getting any data back. Let's try changing the speed down. Maybe it's picking a bad speed that doesn't work with the chip right now. So let's bump this up to 2 megahertz. Let's see if this works. No, we're not getting anything there. Let's bump it down maybe to 0.5 half a megahertz, so 500 kilohertz. And see, I don't think the SPI can do 500 kilohertz for this. Huh, that is really weird. Question, I'm using Python 2 here. That's one good question. What's the difference between Python 2 and 3? So I'm using 2 because our GPIO library only works with 2, and that's because the rpio.gpio library, at least as of like last year, only worked with Python 2. So it's kind of a hard process and it's a little bit slow process. Over time, we're porting everything over to work with Python 3, but it's kind of tough in that if your dependencies don't do Python 3 yet, then you really can't do it technically. But you can write Python 2 code that at least is a little smart and more compatible with Python 3. Like one of the big changes in Python 3 is the print statement. So like in these examples, for example, in Python 2, this is actually a perfectly valid print statement. So if I run this code, for example, it's still printing out everything. Whereas in Python 3, you actually have to have parentheses. But in later Python 2 releases, they actually backported it down, thankfully, so that your Python 2 code can actually look like Python 3. There are a lot of other bigger differences, and maybe I'll do a later stream on that. But the biggest difference, well, maybe not the biggest, but the one I worry about the most is that they actually changed how division works. So in Python 2, by default, integer division is the default. In Python 3, floating point is the default for division. And they actually added a new operator, a divide. So like if I had foo equals, 1 divided by 3, in Python 2, this is actually going to give you 0 because it's just doing integer division. It's going to round down to 0. In Python 3, this is actually going to give you 0.33333, and if you wanted to do explicitly integer division, you have to do divide, and that's a real big gotcha for embedded code, because in a lot of cases when you're doing bit shifting and you're doing division, you've probably written your script to assume that you're getting integer division, because that's kind of the default for like C code. As soon as you run that in Python 3, it's going to run, nothing's going to fail. Like Python 3 is not going to warn you, hey, I'm going to do float division now, but suddenly you've got a floating point value where you probably expected an integer value, and so things explode from that. And so that's one tricky thing where like converting to Python 3, at least for a lot of embedded code like this, is not as simple as just flipping a switch. You really have to run your code, see that it works, figure out, are you using integer division and stuff like that. There's some libraries I think that help with that, but it's still just a big thing to be kind of concerned about. So okay. So for some reason, it looks like I broke the hardware SPI. I'm going to have to come back to this later. I'm not going to debug this more on the stream, but it was weird. We saw it working earlier, and then for some reason, it looks like I've changed something potentially. But real fast then, I wanted to just try putting this onto PyPy, the Python package index. And so let's kind of try that and see real fast kind of the process for it. And maybe since it's broken, I don't want to put it up there when the hardware SPI isn't working right now. So I'm just going to walk through the process, and maybe I won't actually run the commands to push it onto the Python package index. But to do that, so let's see, like I said before, the best source for this, and I'm still kind of new to this, so I haven't done a lot of things on the Python package index, so I'm sure people might see things and say, hey, there's a better way to do this, and that's awesome. But this Python packaging guide is kind of the place to go to find out all this info, and it's great. It's got a great little section here on how to upload your project to PyPy, and if you haven't seen it before, PyPy is the Python package index, and so it's sometimes called the cheese shop, because like Monty Python, and so this has all of your code. And so when you do a pip install, so for example like sudo pip install requests, this is a library for I don't even have pip install, it's sudo apt-get install python pip. The Jessie Lite distribution is what I'm using, and so it doesn't have all the packages installed, but after I install pip, then I can use this to pull down packages. So like the requests library, like I was mentioning, that's a library on the package index here, and you can kind of see all the metadata on here once it loads up. And it's just installing pip right here. So once I install this, then I can install some libraries. But what I want to do is I want to have, okay, yeah, so here it is. So here's like the requests library. One kind of unfortunate thing is the package index doesn't seem to have the best search in the world. At least it's not as good as Google, which that's unfortunately difficult to do because Google has a heck of a search engine, so it's a little tough to compare them to that. But basically, so here's the requests library, for example, and then if I do a sudo pip install requests, it's actually pulling down, based on the metadata here, the requests library. And so it does have, the website here is really nice in that it shows all of this metadata for a library. Like this is the whole change log. I think it actually has like the download files that you want for this. So I want to get my code up here, and the package index or packaging guide tells me how to do that here. So you need to create an account on PyPy. And I've actually already done that. I have an Adafruit Python account that I'm going to use to put these packages under. You create your account. You have to do some setup. I'm not going to show this because you actually have to put your password in here. But you create a little file called this pypirc file in your home directory. This tells pip how to authenticate with the server. It's kind of unfortunate that you have to put your username and password like in the clear here, so you do want to be a little careful and probably lock that folder down to just be readable by you, and just realize that your password is there. Next, you need to register a project, and this is where it gets kind of confusing and where Python has a little bit of work to do, I think, to simplify this. So it talks about 3 methods. You can go to the actual PyPy website, like here, and you can fill in info. Like I can manually say I'm going to create, an Adafruit MCP 3008 library in here, fill in all of these details, or you can put these. It can actually pull these out of your Python library, because in this setup.py, I've actually created all of these. I've set most of these values. And the way it does that is you can actually run a command to generate this package info script, and then you upload this package info. So let's just run this command. So it says I need to run this egg info in my library. So let's run this. So setup.py egg info, and this should create this package info file. So let's see what's inside of here. Nano. Oh, it's inside of the. Where did I put that? Okay, so it's inside the .egg info folder. So there's a package info, and let's see what this thing looks like. So this just has the metadata, like as name value pairs here. So I can create this. I can upload it to PyPy. That's going to fill in all the metadata, so it knows. Okay, now I know that there's a project, with name Adafruit MCP 3008 in here. Or the other options they talk about here, you can use this Twine register. I have not even looked at this. I have no idea what Twine is. It's new to me. I haven't seen this. I remember looking at this last year and I hadn't heard of Twine. So I think they're trying to make PyPy a little more secure, because when you look here, the not recommended option is you can actually run a command right in my folder here. In my library, I can run this package register, this register command. This will actually go and send my data to PyPy. But they say it's not recommended because it's not done over SSL. It's just in plain text. It's going to send your password in plain text. So that kind of worries me. I don't like that. I mean, it's not ideal. So I was going to use the form option. I think that makes the most sense. Twine, it sounds like, is probably what we're supposed to look at now, but a lot of things are changing in the Python space. So maybe next year there's a whole new tool to do this. But basically, these are the options. So you register the package, and then to actually push the package, again, it has a few options. So you can use this Twine tool to do it, or you can use the setup tools command. And again, they say this is not recommended because it sends things in the clear. And so you use this sdist bdist wheel upload, which is kind of weird and obtuse. But basically, this is, if I remember correctly, sdist is building a distribution that's just with, I think, the software. And then maybe it makes a binary distribution also using a wheel format, which you can read the rest of this package user guide to, like, a wheel is a new type of Python package. There's also an egg, which is an older type of a Python package. There are source packages. The Python packaging landscape is a little complicated. It's starting to solidify into, I think, like one set of at least best practices, which this Python package user guide tries to kind of distill. But that's why whenever you look at Python packaging stuff, you're going to start to see stuff like eggs and wheels, and your head's just going to spin. But ultimately, I just keep coming back to this Python packaging user guide because this is supposed to be the truth of like what you're supposed to do. But anyways, you run this command and it will actually upload your library. So it's going to generate the binary versions if it needs, if it has, any like Python modules to compile and stuff like that. It's going to do a source distribution also that has your raw source code and upload that, and it'll make it available here. So, once after I did the register, I could, in theory, just run this setup upload command, and it would send my package to the Python package index. I'm not going to push it just yet, just because I noticed something's broken in it, so I don't want to push out a broken package just yet. I don't want someone to pull that down. But eventually, so for example, like one package that we just recently put up is Adafruit.io. So if I do sudo pip install Adafruit.io, and this is the Adafruit.io client, so this is the Python client to talk to Adafruit.io, and this is just going to work. It's going to pull down the package, and you can see it's kind of installing. Oh, that's cute. Oh, it's mad about something. Install. Oh, the required version of setup tools is not available and can't be installed while the script is running. That's kind of an annoying error. So sometimes Python things don't have the best error messages. It would be nice if it down here would have said, hey, you don't have the right version of setup tools. So to fix this, I think I need to do, let's see if this works. Sudo pip install, and let's just do help, because I think I need to run an upgrade command. Let's see what happens here. It's running really slow for some reason. Okay, this is going to tell me everything. I think there's an upgrade command where I need to tell it to explicitly upgrade, which is another thing I don't like. Like if I'm installing a package, I probably want the most recent version, but you explicitly have to tell it that you want to upgrade. What is this thing telling me? Let's see, where are the options for this? Oops. Okay, install options. Yeah, here we go, upgrade. Upgrade all packages to the newest available. So let's try this. Let's try, oops, wrong folder. So let's go down and let's do sudo pip install setup tools upgrade, and let's see what this does. This should in theory give me the right version of setup tools. It's kind of good to go through this because this is a common error that you're probably going to run into. You're going to read a tutorial that says pip install this package, and then you run it and it fails, and it's like, what the heck's wrong? So you have to go back to the error messages and see. So okay, looks like it installed it. Yeah, found existing 3.5, uninstalling, successfully installed. Okay, I think this is going to work. Let's try this again. So let's see if we can install the Adafruit.io library. So it's downloading it, running setup.py. Okay, this looks like it's working, I think. Let's see what's happening. So it's installing the Python client. Installing Paho, that's a little MQTT library. Okay, success. Okay, that worked. So at least that's an easy fix. And I'm glad that I could kind of show some of the debugging for that. But that's an example of an Adafruit library that we have on the Python package index. So if I go back to the package index in here, and if I search for Adafruit.io, this should come up, and you can see, yeah, here's the metadata for it. And this I loaded onto PyPy using the exact same commands in this Python package guide here. So using this bdist upload. I'm going to have to look at this twine command. I mean, it looks like this is the new thing that everyone's supposed to use, so that's probably the way to go with it. So I think that's all I wanted to show, is just kind of some basic library creation, adding some stuff, talking a little bit about SPI, and then also getting into how to upload this onto the Python package index. And unfortunately, there's something wrong with this code, so I'm going to have to debug it, but I'll get a version up on the package index and we'll be able to use it. If anyone has any questions or anything, maybe shoot them into the Twitch chat right now. Let's see. So, let's see, product suggestion, a TI CD4052 BE-based breakout to multiplex serial lines so you can have multiple serial devices on a Raspberry Pi. That's a good question. Good point. Yeah, like, the Pi only has, I think, just one hardware serial line for this. That could be kind of cool to have a breakout. So yeah, it sounds like there's probably different chips out there that let you multiplex serial. Cool thing to definitely suggest it to folks, because that could be useful. Like if you have multiple serial devices, like GPS devices, sometimes they're serial. One thing is like the little the PN532 NFC card reader that we have. That's a nice device. It uses I2C, but it uses clock stretching, which is maybe a whole nother video. And that's functionality that actually doesn't work on the Raspberry Pi. There's a bug actually in the firmware, and you can find in the Pi forums where the Pi designers kind of figured out the issue. So Clock stretching is a functionality you can do with some I2C devices. Some devices require it. Some devices it's optional on. The PN532 requires it, and so unfortunately it's kind of tough to use it on the Raspberry Pi. And as an alternative, it has a serial output, so you can use it. You can connect to a serial port and talk to the PN532 that way. Let's see, other question. Are we planning to write an MQTT bridge tutorial to connect a local MQTT to Adafruit I/O? That's a cool idea, I think, so you could run your own local MQTT server, like maybe just something within your own network. You've got all your devices talking to it, and then have it be a bridge up to Adafruit I/O. What you should look at is actually the Mosquitto MQTT server. Mosquitto is really nice. So let's go to it's kind of the reference implementation of a MQTT server. So it's open source. I think it's actually owned by the Eclipse Foundation now, or at least they kind of gave it to them to maintain. And it's great. It's a little MQTT server. Now you can configure it to be a bridge where it acts as a server locally, and then any things that get sent to it, it can relay up to another MQTT server. So definitely look at Mosquitto. Check out like its configuration. I think I've actually set it up once or twice like this, and it should actually be able to just relay straight to Adafruit I/O if you configure it to use the same MQTT server address. Give it the correct login, like your username has to be your Adafruit I/O account name, your password has to be your Adafruit I/O key, and then you could relay messages. Now you would probably need to be careful because Adafruit I/O it expects if you want to update a feed called foo. I'm trying to remember the exact path, but you have to do like /feeds/foo. Whereas if your local MQTT server gets a value that's just under the /foo path, it's going to try to send that to Adafruit I/O. It's not going to mean anything to Adafruit I/O. So you might have to do some fanciness around like maybe filtering out messages that don't matter. But yeah, that's a cool idea to maybe do that as an example. So. But yeah, I think that's it for this stream. Looks like no more questions and stuff. So thanks a lot for watching. Subscribe to the YouTube channel and you'll be able to watch this later and all kinds of other cool videos. So subscribe to Twitch. You can watch this live when I stream it. And then I'll also mention, so I was using the Raspberry Pi Zero for this. There's a contest going on with Hackaday. So if you come up with an idea for a cool Raspberry Pi project that uses the Zero, you can get a chance to win a Raspberry Pi Zero or other fun stuff. So check out it's Hackaday. Basically search for Hackaday and Adafruit Pi Zero contest and you'll find it. So that's that. Thanks for watching, and I guess I'll see you guys hopefully next week. We'll do some more streaming of some cool stuff. So thanks a lot.